The buck converter, as I told last time, it starts with the switch here, okay, where we can we can cut the input according to the frequency of open and close, on and off for this switch, to make V out at this point here, or to make V in at this point, similar to square wave like that. By doing this, the V out is the average of that square wave. So if you open more your duty cycle, you make this one closed more time, and more than 50%, you are going to increase V out. It's the average. Yeah. Okay, 1 second. Let me just open this in Adobe Acrobat here. So you can write on that paper. Where is it? Okay, so we have our input. That's your Vin. Now the Vin will go through that switch, so we'll allow that Vin to appear here for a certain time and disappear, appear and disappear, and so on, like that. So by doing this, we'll at this point here, this node, we'll end up with the curve like this. Okay. Now that one here, this is on. Once this one is on, means conducting, or off, closed here. Now the average of this one, if it's 50-50, so the average will be half of that. The average of any curve like that means this area, cannot maybe write inside, but I'll go from outside and come back in. No, you know, this area here should be equal this area. That's the average. Now imagine if we keep this switch on more than 50%, what will happen?
On time will be more.
Yeah, and the average will go up. Why? Because this area now, it's more open, which is equal to this area. We multiply this part with this part here, and this part with this one. You'll find the sections, they are, or area, they are equal. A1 equals A2. So this will be increased. The V out will be more than this V out here. If you reduce, if you open this one for short time, and you open more time, like this, V out will be smaller, something smaller like this, because this area will be, this area here will be equal to the other one here. And this how we can adjust V out, increase it, decrease it according to our needs. Okay. Now once we open this, let's say for example 50%. So 50% Vin will appear here for the rest of the circuit. And if Vin is here, so the positive plus for that Vin will be in this side of the diode, negative will be here. And what will happen to this diode? Will be blocked, because high potential is this side, the anode, the cathode, sorry. And the anode is low potential, means this one will be blocked, will be open circuit. So the last circuit, once this one is conducting, you'll be having V in, L, C and R parallel to C, and so on. There is no diode in the circuit. Once we close that, that means we make it open, not conducting, this switch. Okay, so now while this one, before we open that one here, while this one was closed, the current is going through this inductor and it's charging that capacitor. This will save energy in it. Okay, now this one is not conducting. That V or this current, this energy will look for a path to discharge itself. So the only path is CR, but the diode now, because this one will be plus here and minus here. So the diode will be conducting like this, and will not have any more that section once the switch is off. Okay, so we have only L, C, and R, and L will be try to discharge itself. This one here, R, will see all the time V out, because at the beginning, R, a transistor closed. This one has its maximum that can be charged, which is V out. This one open here, not conducting, the current will continue, and V will be C will be all the time charged through from this energy here, and V out will be all the time same to this in terms of average. So V load will see all the time its average here, V out. That's why I made the straight line here for on and off. But if practically, even in simulation, it goes up and down like this little bit. Okay, with certain ripples. But I'm talking about the average. The average is that line here. But V out will be, you see it, it's up and down, and this is what you call delta V. And here, that's why I'm asking you down here that the delta V, the ripple here, should not exceed 1%. Okay, and this V max and V minimum here, okay, the difference between them should not be more than 1%. Okay, how you can find this? In your simulation, with cursors, you can measure delta V naught. We call this one V naught, and you have your V naught. For our case, should be 12. If you divide it by V naught, this will give you the percentage of that. Keep in mind, delta V, that this one is volt, and V is volt. That's why the ratio will be unitless, and you can express it in percent. So if you have given like any ripples, voltage ripple in volt, means delta V. If it's given in percentage, means delta V naught over V naught. Okay, so the one here we're asking for you, which is 1%, this means delta V naught over V naught, not V naught. V naught, which is V max, which is in volt, minus V min, which is in volt. So the result will be in volt, not percent. But if you divide it by the average, will be in percent. Is that clear, guys?
Engineer, here you mean 1% of 12 volt, yes?
Yeah, it should be 1% or 12 volt.
It should be, you mean peak to peak or plus minus?
No, peak to peak. Look, delta V naught, that peak to peak like this, should be equal 1% if you multiply this by this of V naught. Is that clear?
Engineer, I placed all the parameters. It did match the 1%, but not peak to peak. It was like very close to it, but little bit more. So maybe 1 point something %.
Yeah, I'm going to talk about that.
I don't know if I can show you later.
Just let me continue explaining this the theory here, and after that you can
Okay.
one by one. Okay, I need to give you one thing also. Now, is that clear, the theory here about the first part? Okay, let's talk about the next part. How we can find, how you should
Doctor,
design.
could you record?
Yeah, it's recording. It's recording, but
Okay.
using my my software. Yeah. Okay. So we have this inductor and the capacitor. We have a formula how you can find them in your textbook. But let's talk about this right now. I'll give you tips. Okay. Now, first of all, once you need to design. Now I'm talking practical wise. Okay, not theoretical wise. If you need to design your circuit, first of all, you have to define your switching frequency to be used, okay? And after that, your controller to be used and so on like that. So first thing to be defined is the switching frequency, because everything will depend on that. We didn't give you switching frequency here, but through the theory, we need you to understand how you can find it. You can, select appropriate one. But since I'm explaining, I'm going to give you one tip about this. Let's open my whiteboard here. That one. Okay. Yeah. Okay. Our switch, our DC to DC converter, the buck converter. It's this box here. Okay. Inside the box, we have a switch, we have a diode, and you have inductor. Those are the main parts of your DC to DC converter. Of course, DC to DC converter. Of course, inside, but I'm going to put it outside here. Let's put it inside. Okay, we have a capacitor. So this capacitor is just to adjust your ripples, the required ones. And outside you have your load like that. And we call this one a power stage. It's very important to memorize this or understand that. So that's the power stage. Okay, here, that's your input. Can be a battery, can be a solar panel, can be something else. Okay, wind, that's wind thing. Energy coming from the wind, and so on. And your load here can be resistive, can be something else. Okay. Now that's the power stage. How we can control this? How this will work? Of course, will work if we add the control part. Okay. So this is that controller, which is a microcontroller. Okay, should be added. This is a microcontroller, not a micro capacitor, micro C or something. So this one, your microcontroller should be connected to your switch. So this one will generate pulses. Okay, you can write your code and you give your duty cycle and your calculations, and this one will generate pulses. Those pulses will be given to your transistor. Okay, the transistor to be used, it has let's say collector here, emitter and base, for example. So sometimes you call this one a source. It depends on the transistor. So those pulses will be given to your switch. Now, let's say all microcontrollers, most of them they generate pulses, maximum 1 volt. 1 volt as maximum. Okay, here. So of course, that switch cannot be open and closed by 1 volt. So what we do, we add one stage and we call this one gate drive. Okay, that gate drive has two jobs, two tasks. The first one is to boost that signal, take that signal and create image of that signal. Image, should not have any delay or something, so copy paste. With the maximum here, we'll boost this one to, let's say 12 to 15 volts. That's the first task of this gate drive. The other task is to isolate the microcontroller from the power stage. So control from power stage should be isolated. Why? Because this one will be affected by the ground to your power stage, because this is you look at this one like a simple circuit, but if you connect your real device if you use it, of course this one will be connected to we have like rectifier, and before rectifier we have a socket connected to single phase AC socket. That socket has connection with other customers around. Those customers, if they have any ground problem, it will affect your power stage. If there is no isolation, it will affect your controller, and the controller will trip, will stop, and no pulses will be given to your circuit, and everything will shut down here. So what to do? We have to include like small transformers inside. Those transformers will do that job. Will isolate to create like a ground to this part, and the other ground will be that part. So two grounds in your circuit, separate grounds. So that's the job of this gate drive, and those pulses will be now given to your switch. We'll go there, not this way. Sorry. Your pulses will go this way here. Okay, so that's. I hope we can have time during this semester to do a small one like this. It can show you how you can design your PCB, the printed circuit board, the PCB, and how you can solder your components. All we need here is switch, diode. We can design our own. We can make our own inductor. Capacitors, we have them in the store, so we can use them. DC, we have DC supplies, and the load, we have a load. Controllers, we can use embed. You can use DSP controller. You can use embed controller, for example. So to generate those pulses, it can give you gate drives. You have them. So maybe you can use. I can design one session for that, and we can use it. Physically, you can connect your oscilloscope here, and you can see physical, real signals, not simulated ones.
Engineer, how will we do this practically for the pulse generator?
This one here?
For the pulse generator, yes. Practically, how can we do it? By using the oscilloscope, yes?
No. We can use. You have to use your controller. Actually, I'm using a DSP. This one here. For your case, maybe you can use embed for small application. You have used embed before, maybe in other course like that embedded systems or other course. So you're familiar with that one. You can use this one. I'm going to design one and check it if it's feasible or not, and we can use it. We can do it. Just designing one converter, let's say a buck or boost converter, one time, you'll be ready to design the other ones by yourself in terms of physical design. So now let's continue. I did all this just to explain just to explain the switching frequency, how we can select that one. Switching frequency, you can select it. It has a big range. You can select it as you like. You can increase it. There is no limit. Theoretically, no limit. Okay. Okay. By increasing the switching frequency, you're minimizing the size of the die of this inductor, and this is needed. This is required in all designs because we need to design a small device. That's why small components will make small device. So to have a small inductor, we increase that one. You keep increase this one to minimize, make it micro size for this inductor. But, and big but for that, there's a compromise for this. There's a limitation practically, which are those two here, the gate drive and the microcontroller. The gate drives and the microcontroller, sometimes they don't accept, they don't tolerate something like more than 100 kilohertz, for example. Okay, so you can make this one, you can make it 1 megahertz. Okay, this one will be smaller, we'll be happy. But once you go to the practical part, this will not work. Those two here, the microcontroller and this, because you design or selected your switch switching frequency. Okay, so for your design from now on, you can select your switching frequency between, let's say, 10 kilohertz. Okay, I have my design, my actual design in the research room. I'm using 10 kilohertz. Okay, so your switching frequency can be between that and the maximum 100 kilohertz. In the literature, the textbook, you'll find them using like 400, 500 kilohertz. But this is for the calculation only, for the theoretical part only. So just to be realistic and take something in between 10 and 100 kilohertz to design your cell. Okay, now this is step number one.
Engineer, please, before you continue, so just to confirm, we use from 10 kilohertz, around 10 kilohertz to 100, so that to have the inductor small, or to have the circuit small, or I don't know. Can you repeat this, please?
No, if we increase that, if we make it bigger than 100 kilohertz, this will be smaller. But we have a problem. We'll be happy with this to be smaller, this inductor, but the gate drive and your microcontroller will not be happy because will not work. It's over. Okay, this will go over their limits. So that's why we have to accept that the inductor will be a little bit bigger, but the controller will work. You have to put yourself. You have to satisfy the inductor in terms of size, and the microcontroller and the gate drive in terms of acceptable switching frequency to work with. I think it's clear, right, Muhammad?
Yes, it's clear.
Yeah. Okay, so now this is for the switching frequency. Once it's decided, you decide for your switching frequency, and I believe that from group to group, the switching frequency will be different. I mean, your groups here. After that, you can start using calculating your duty cycle. For our case, will be this one. So this in percent. And now, since we don't have microcontroller, we don't need them, microcontroller and gate drive, because we are working on Simulink. You can look for pulse generator block. Okay, and there, once you double click on that block by default will give you like a V. The V for that is 1 volt. That's why I told you it's 1 volt, the pulses. And duty cycle, it's written in percent. You write there 40, 45, it depends on your calculation here. Write that number, and this will be ready to generate those pulses You have just to connect that block. It's a block like this. It has only one output. You take that line and you connect it to your switch. Okay. You switch the switch. You know, and how you can find the switch in Simulink. You connect it there. Just be sure, please. If it's not working, be sure on the polarity of the switch. All the time, the plus of the DC should be connected to collector, not emitter, because emitter will be like a block. There's no current will go there. Okay, and emitter will be connected to the rest of your circuit. Okay, the other leg here will be connected to the pulses here. Yeah, this for the switch, and that's for the duty cycle. Inductor, I think you have to find your inductor. We design everything at the beginning, or from the beginning, that to find L minimum, because the inductor, the value of that one will decide for our DC to DC converter to work in continuous conduction mode or discontinuous conduction mode. Continuous conduction mode, which is the currents going through that inductor. So you have to check that one. You have to put like now a meter here and connect it to your oscilloscope. Okay, and check the waveform. Delete that. The waveform should be something like this. I mean by that, your minimum here should be far away from zero. Or if you calculate the minimum value of L, means your current should touch zero and go up. So to do this, you have to calculate your L minimum, and L minimum, it has a formula that you have. I give it to you, which is 1 minus D times R, your load, divided by 2 and the switching frequency. Depends on the switching frequency you selected. The D is calculated, R is calculated. We're giving you the load since 2 amps means 12 volts divided by 2, that's 6 ohms to be used here. And you have this, you have everything. You can calculate L, and that's the value that you have to put in your inductor here in your Simulink. Okay. Now, usually in practice, now this is for design. In practical part, we add we find this value and we increase it a little bit, like 25% more than the designed one, just to be sure that, because the microcontroller will not be will fluctuate a little bit in terms of control, and maybe you can go below this zero here. So to be sure that will be in safe side, once you calculate your L minimum, you add 25% to it, and your current will be up above that x-axis a little bit here. So be sure that anything happens, if that fluctuation here, this current goes down a little bit, it will touch zero but not below zero. Okay, if you get something like that, you have a portion with zero and going up and down zero, and like this is what we call discontinuous conduction mode. We don't need it now, but this part is needed for some of the applications. For our case, we stick to continuous conduction mode, please, either this one or that one. Okay, now that's for how to select your L and how you can verify if it's in conduction, your whole system in continuous conduction mode. Now about delta V, the ripples. Okay, this will be determined by the selection of the capacitor, right capacitor. So the value of the capacitor, it's I'll give you. I'm looking for the formulas also, just to be sure that I'm giving the right formulas. 1 minus D divided by 8L, which is L you have here, and the frequency, switching frequency squared, and multiply by delta V over V naught in percent. Okay, this is in volt, but in percent, that's V naught over V, delta V naught over V naught. So you have everything here. L calculated before, switching frequency selected, the D calculated. This is given or required. Okay, you can request it by yourself. If you don't like 2%, you can make it more squeezed than 1%. You can, if you don't have, you cannot find this value of C, so you can increase that one. By increasing this, we are decreasing the size of the C. If we need delta V over V naught to be more tight in terms of ripples, we have to increase C. But sometimes increasing C will make it in terms of size any big. Okay, so we have to accept one of them: big size, small ripples, or small size, big ripples a little bit, or you can put everything in between. Okay, so this is a C and calculated C. So we have everything in here. You have C, L, you have your R, you select the diode, the switch, you have your battery here, and you can start your simulation. Now, once you do your simulation, I'm pretty sure 100% that as open loop, you'll find something in it. Of course, and don't look at the transient phase. The circuit will do, and remove this. Okay, the circuit will do something like this and go to look for steady state like that. So you judge your circuit in that stage, not here. That's why in the lab manual, we are asking you to plot the 5 switching frequencies. You go to steady state, okay, in this part here, and there you can zoom, you can just screenshot 5 switching frequencies and plot them for your report. Now here, once you zoom in that one, like this, if you zoom and you check, it looks, once you have everything in front of you, it looks like one line. But once you zoom, you'll find them going up and down like that. And there you can calculate that delta V naught in volt. You divide it by V naught, and you can check if it's 1% or less as required in your manual. But that's the very important thing. Once you look at the average of that one, you will not find it. I'm 100% sure you'll not find it 12 volts. You'll find it something below of that. So what you have to do, okay, if I tell you that D equals V naught over Vn, so V naught will be equal D Vn, صح? Or V source. This is Vn or V source. Anyway, that's Vn and Vn here. If we need to adjust this, what you have to do? Hi, Muhammad, or any one of your colleagues. You have your formula.
We can increase the D, so we can increase the other one.
Why not Vn?
Because
yeah,
I mean we need to reduce the Vn, so
no. Look, it was tricky question, but Vn is constant. It's your battery. You cannot change it.
Yeah, that's what I said. I mean, we need to reduce it to the 12 volts. It's already constant at 20. We can't change the 20.
You cannot change it. Yeah. So the only parameter to change, to adjust, is D. صح? Right?
Yep.
Yeah. V naught equals D. That's V naught times constant. So the only parameter to adjust is this one. Constant, I mean by this one, is V in, which is your battery, your input, which is you cannot change it. It's fixed. So the only parameters to adjust is that one. So if in your design, in your simulation, you find this one to be below 12, what you have to do, you have to go back to your simulation, which is in your post generator here, and try to increase a little bit this 40 here, or whatever you found at the beginning for your D. You can increase it a little bit, not more, not by tens, but by fractions, okay? Fraction by fraction, you can increase it and double check again every time till you reach the average to be 12. This is done manually because it's open circuit. It's open loop, sorry. So open loop, we have to do it by ourselves. Double click on this pulse generator and change this, change the D. But if it's a closed loop, in case if you have a chance to do it after, so we have to have a feedback here from this point. Okay, we do like we have a circuit to get the feedback from this V and send it to our microcontroller. In microcontroller, we give a V reference. It's like your cruiser in your car. Don't know what is happening here. V ref. This is ref. Okay. So you give your V reference. For example, in your car, you need to run at 120 kilometers per hour. So you fix it in your cruiser, and your microcontroller, the car microcontroller, will increase, decrease, or push the gas or reduce the gas till it will get the speed at this value. For our case, same thing. We give in our code inside my controller, I'd write this one to be 12 volts, for example, and this will be compared by our microcontroller to the feedback. The error here should be 0. If it's 0, means feedback equals the reference, and that's what we need. If it's more or less,
Engineer,
yeah,
you can continue. I will ask after you.
yeah. If this one different than 0, more or less, this microcontroller by itself, it will adjust the duty cycle by itself. Okay, just it will increase more on or less or more off state here or a time in order to adjust the average of the output to be 12 volts. This can be done if we have closed loop. Open loop should be done by ourselves. Okay, I think I will stop here because I have a lecture maybe at still you have at 11. Yeah, do you have any question? Go ahead.
Yes, engineer, I have one question about the open and the closed loop. Can you repeat when they happen? Like when we will be in the closed loop and when we will be in the open loop? I did not get them.
Yeah, open loop as beginners. Just we study like that in the circuit like this. But closed loop, if you need to sell your product, should be with the closed loop because nobody will accept that one. Look, if closed loop, when we need the closed loop exactly, because sometimes the input will change. You remember, just okay, let's do it here in this section. We have our DC to DC converter. Whatever type of DC to DC converter, can be boost, back, or anything. For our case, as a beginners, we put like at the input here, we fix the battery, but in reality, inside we have or before that one, we have rectifier. We have rectifier, diode rectifier here, for example, and this rectifier, of course, your circuit, the whole circuit will be connected to a socket, which is single phase AC socket. So this rectifier will take that AC here, will rectify it with this, will rectify that one with this capacitor. Will make it a little bit smooth, like a DC. So that DC will be given to our DC to DC converter, and there we can adjust that value. You can increase it, decrease it, and so on like that. Okay, to satisfy our load. Here we have two parameters that suddenly they can be changed. The AC كهرباء, they can have any short circuit, any problem, that 240 volts can go up or down. So here this will follow that output here, because this one is not controlled. It's a diode, for example, and this Vin for our DC to DC converter will follow that change here. Will go up or down. By going up and down, V out will follow also. You remember it's direct relation here. Okay, V out, it's a portion of V in, dV in. So if V in goes up, V out goes up, and so on. It's the direct, proportionally. This one proportional to the other one. Or if this one is fixed, for example, the load, and sometimes it happens, the load, and it has any problem, and it will be reduced or increased. It depends also. So we have two parameters: the load, I mentioned by load here R, and the V source, the source coming from the socket. Two parameters to change any time. Okay, so for our case, to avoid or to just let the load or the controller here, sorry, this DC to DC to not see that changes, we do it in closed loop, through closed loop here, and the microcontroller will tell our microcontroller we need all the time to keep this one 12 volts. Whatever happen in and out, keep it 12 volts. He will adjust himself to keep this one to 12 volts.